Okay, well, that's a great segue. Yeah, we're going to pick up with example 24c. We didn't quite finish this one, but it was pretty easy to go from here. Integrate, substitute back in because it's an indefinite integral. So 24c, your mental flow chart, you might do this to start: 2 integral x plus 1 squared dx, and you might be like, okay, it could be a power rule. Let's see, the derivative of x plus 1 is 1. That's not x, so we're off by a variable, and x plus 1 is linear, right? -2. Thank you. Oof, that would have been, yeah. When you bring something to the top, change the sign of the exponent, right? Okay, good. Thank you for catching that. This is then a good candidate for u-substitution. So off to the side here, we'll let u equal x plus 1, so du equals dx, and x equals u minus 1. So that's essentially what you're going to have to do. You're going to have to solve for u, you're going to have to solve for dx, and you're going to have to solve for x. Those are kind of the three things. Now, replacing it underneath there, the 2 is a 2, so x becomes u minus 1, x plus 1 to the negative second becomes u to the negative second, and dx and du are just a straight exchange, right? So nothing else needed there. Now what? What's the next step? Distribute, right? So expand or distribute. In this case, we can just distribute. There's no squaring going on. So we get u to the negative first minus u to the negative second du. And now it's just power rule time, right? Unless it fails. What does u to the negative first become? Very good. That's where it fails. So natural log of the absolute value of u. And that becomes u to the negative 2 plus 1 is negative 1. Times the negative 1 makes that plus. And then, of course, you could put the plus c on the inside, but times 2 makes it ShamWow c, so we'll put it on the outside. And this would be really unfortunate if you decided to stop here, right? Because it's an indefinite integral. We have to put it back in terms of x. So what is u? X plus 1. So this becomes 2, and I'll go with parentheses now, the natural log of the absolute value of x plus 1 plus 1 over x plus 1 plus c. And you're done. U-substitution, when your inside function is linear and you're off by a variable. Now that's like 99% of the time you're going to see something like that. But there are other times where U-substitution will work. If you remember, I said when your function is degree 1 or smaller. Degree 1 is linear. Sometimes, though, you might have a smaller degree. Now, when you're doing U-substitution, would it ever make sense to replace x with u? If you do this substitution, is anything ever going to change? No. So it's only beneficial if you have something that's more than a plain old x, like more than one term, if it's linear. But there are exceptions to that. Okay, let's look at this guy here. If you wanted to rewrite it, you'd probably write it as the integral of x to the negative 1/2, 1 minus x to the negative 1/2 dx, right? That might be your first step. Your mental flow chart would be to look at probably the more interesting inside function, which is 1 minus x. Its derivative is what? Negative 1. Is that anything close to x to the negative 1/2? No. And of course, the other inside function of x is going to be off as well, big time. So that's not going to work. So we got to use U-substitution here. The correct choice of the inside function is 1 minus x, because remember, if you just let x be the inside function, replacing x with u is going to get the exact same thing, except with u's instead of x's. So let's see if that works. We'll let u equal 1 minus x. So if you want to solve for x first, instead of going du and then solving for dx, you're going to have to solve for x anyway. You might as well just solve for x. You get 1 minus u. So if you want to solve for x first, sometimes it's easier. And then take the derivative of both sides using differential forms. So dx equals negative 1 times du. So dx is negative du. So that'd be the fastest way to kind of get everything you need. U equals, then solve for x, and then take the derivative. And now we'll do our replacement. That becomes the integral of x, bless you, which is 1 minus u to the negative 1/2, times 1 minus x is u to the negative 1/2, and dx is negative du. So we do that. Now, if you compare what we started with on the line above to where we are now, does it put us in a better situation, a better circumstance? No. In fact, it's pretty much the exact same situation, right? Because once we have u's and du's, it can essentially be x dx. So we essentially have a 1 minus u to the negative 1/2, which is what we had before with 1 minus x to the negative 1/2, times u to the negative 1/2 is like x to the negative 1/2. The only differences are negative 1/2 front. So all we did is just kind of go in a circle there. It didn't really help us. So, not that this is wrong. This is still correct. It just doesn't help us find the antiderivative. So, like Thomas Edison, we will just say that we successfully found something that doesn't work. Right? Bless you. And since we're looking for inspiration, and it's 99% perspiration, or something like that, wear deodorant. I don't know what he said. We'll try something different. What? Oh, okay. Let's try putting them under the same radical. Dx square root of x minus x squared if you distribute. Is that going to help us? Unfortunately not. What if you completed the square under the radical? Could you complete the square under the radical? This is a good candidate for completing the square, right? Let's try that. I've never done it like this before. Let's see if it works. Bless you. It kind of looks like it could be an arcsine or an arcsecant at this point, right? So if I completed the square, I got negative x squared plus x. I'll do it off to the side. I got to factor out that negative x squared minus x plus something. And then I'm going to go ahead and say plus something on the outside. So half of negative 1 is negative 1. Half, negative 1/2 squared is positive 1/4. So what I really did here is I didn't really add a 1/4. I actually subtracted a negative 1/4 because there's a negative there. So out here it has to be a positive 1/4. And if I do that, then that's 1/4 minus x minus 1/2 squared. So would that work? Let's see, we'll put the dx out there. We got a 1 here. You got a 1/4 minus an x minus 1/2 squared. I think it's going to work, right, with the radical. So if I do that, let's see. We'll see if it works. If a squared is 1/4, a is 1/2. And if x minus 1/2 squared is u squared, then u is x minus 1/2. Here's the thing that's ultimately going to make or break it. What's the derivative of x minus 1/2? 1. We're not off by anything. So, being arcsine, do we have a 1 over a in front? No, we don't. So it just becomes arcsine of u over a, which is x minus 1/2 over 1/2 plus c. Which if you distribute that, that's arcsine of 2x minus 1 plus c. It worked. So there you go. That was pretty resourceful. That's the way you did it last. No, I don't think I've ever done it that way, because I've never tried that. I don't see things that way. But you offered it up as a suggestion, and we went with it. And software update, no thank you. Yeah, so cool. That's kind of what's fun, is you don't really know if something's going to work. You just kind of see something, you try it, and if it works, it works. If not, you've kind of gained some insight from why it doesn't work. So, no, this is what we're supposed to do. Succeed. We did. Yeah. But let's explore some other options, right? So we found one method that works. I like that. Is that right? Did I miss a constant or anything anywhere? No? I don't think so. It looks good. What's that? You take half of the coefficient. Half of negative 1 is negative 1/2, and you square it. And because that's a plus 1/4 of the inside, when you distribute it, it's actually a negative, so that becomes a positive. Yeah. All right, so let's look at another way to do it. Here's another way to do it. You could do u-substitution. But in this case, you're going to let u equal the square root of x. Now, normally you don't want to replace u with a single term if it's linear, because then u just equals x. It's not going to really work. But in this case, you're replacing it with something less than degree 1, x to the 1/2. So now, instead of taking the derivative of both sides, I'm going to go ahead and solve for x. By squaring both sides, you get u squared. And now dx equals 2u du, right? So this is one of those times where you can let u equal a single term, but it's less than degree 1. It's degree 1/2. So if we start making our substitution, dx in the top is 2u du, which looks like to do. And then the square root of x in the bottom is u, and you get the square root of 1 minus x, which is 1 minus u squared. Now what happens with your u's? They disappear, and you can bring a 2 out front, and then you're left with 2 integral of 1 over the square root of 1 minus u squared du. And now it's like, holy moly smokers. What are you staring at right here? That is straight up an arc sine, right? That is straight up arc sine. That is not even like the pattern recognition arc sine. That's just arc sine. That's 2 arc sine of u plus c. And of course now, because it's an indefinite integral, what is u? U is the square root of x. So it becomes 2 arc sine of the square root of x plus c. And that's not quite the same thing we got over here. Oops. But it is another, I deleted it. There we go. It is another equivalent answer. I get it. There we go. I just wanted to put it side by side. There we go. So notice it did turn out to be another arc sine. But the other way was kind of interesting. Remember, two functions can have different antiderivatives, but then they would only differ by a constant. You would have to do something kind of creative here. There's like, there's no arc sine identities, but if you set it equal to y and then use some sine identities to try and get the angles the same, it's going to come out to be equivalent, but for a constant. So I'm not going to try and prove that those differ by a constant. Yeah?
So on the AP exam,
I doubt on the AP exam you would see a question like this, first of all. This one is probably maybe one step outside an AP exam. It's not outside what you might see in college or like on aisle 5 of the grocery store later in life. So it's kind of good to know how to do this, even if it's not going to be on the AP exam. But typically on the AP exam, the u-substitutions that you're given are linear functions. So I'm just kind of giving you extra examples. But I know what your question is. How would you know which way to do it, right? Because it's dramatically different. I think the method we did at first would probably be the more obscure of the two. And so the u-substitution, if this is on the test, it would probably be this answer here, the u-substitution answer. Yeah, or they might specify letting u, that's how this problem could appear on the AP exam. They would say using the substitution u equals the square root of x, kind of tipping you off. Yeah. Now, having known twice now by two different methods that it was an arc sine, you might be able to wander up to the problem and say, I knew it was an arc sine to begin with, right? How'd you know that? Well, I saw a radical, and I saw a number minus function. And so if 1 was a squared, a was 1. And if x was u squared, then u was the square root of x. And what's the derivative of the square root of x? It's 1/2 x to the negative 1/2, also known as 1/2 times 1 over the square root of x. And that's exactly the other factor. And now I ain't off by nothing, right? Except a half. Except a half. And so now we would have 2 going along, or 2 as a correction, sorry. And it becomes arc sine of u over a, which is the square root of x over 1 plus c. Yeah, I know what, right? Because normally we're used to seeing like a number minus some even power of x. But really, all it has to do is fit. If that is u squared, then u is the square root of that. And if it's not an even number, like 2, 4, 6, 8, you just take the square root. So that's kind of a more obscure way to see it. So anyway, pattern recognition, u-substitution, completing the square. I like it. All right, letter E, another one that is probably one step outside an AP exam, unless, as Katie said, they give you the substitution. But in this case, if you let u equal 2x, you think that's going to be the substitution? No, if you let u equal 2x, if you're replacing u with a linear, it's got to be like 2 terms. That's the power of u substitution when you're replacing it with linear. 2x plus 1 would work, or maybe even x plus 1. But u equals 2x, it's just going to change. It's going to give you the exact same thing, but maybe a coefficient out front. So what could we then call u? The square root of 2x, right? Which would now be something to the 1/2 power, still less than 1. So that's when single terms make sense to call u, when it's not just a linear x, right? When it's the power less than that. So if you square both sides, you get u squared equals 2x, and x equals 1/2 u squared. So again, it's easier to solve for x and then take the derivative, then take the derivative, and then solve for dx. So now dx is equal to what? What's the root of 1/2 u squared? U times du, if you do it in differential form. So now making our replacements, you get the integral of dx on the top, which is u to u. And at the bottom we get 1 plus, what? U. Yeah. So if you want to pull the du off to the side, now it looks like that. Okay, so now we kind of reassess our mental flow chart. It's not a natural log because the 1 plus u's derivative is not u. Would you do another u substitution now and let v, you would go to v maybe, would you let v equal u plus 1? I wouldn't. Because I have another strategy that is kind of like in my head that I'm thinking about using. That was bad. Any ideas? When you have polynomials, linear, quadratic, cubic, and the degree of the numerator is greater than or equal to the degree of the denominator. Is that the case here? U to the first over u to the first. Can't split up the denominator, so you can't say it's u over 1 plus u over u. Long division works here. Yeah, long division. So here we go. U divided by u plus 1. You want everything to be in descending order. U divided by u plus 1. How many times does u go into u? Once. U goes into u once. And now you distribute. 1 times u is u. 1 times 1 is 1. You subtract and you get 1. Does u go into 1? U doesn't go into 1. It would be negative 1. Thank you. I was thinking of my poor grammar joke, and it wasn't even that funny. But yeah, stay focused. Stay focused. All right, so again, what do we do with these remnants? Well, we rewrite the original integral, which, remember, this is already like method 2. We're 2 methods into this one problem. It's the quotient 1 plus the remainder, which is minus 1 over u plus 1 du. And now it's like, yeah, it's like the cat. It's in the bag. And now we should let the cat out of the bag. Don't be putting cats in bags. Why is that even a saying? Or you let the cat out of the bag. Don't put cats in bags, right? Well, if they're alive, I should say. Maybe a bag is the proper way to dispose of a non-living cat. But then why would you let the cat out of that bag, right? It's like, that's where it's probably going to stay forever. I don't know how some of these idioms come into existence. Okay. But now I have 2 terms. Yay! And here we are. What is the antiderivative of 1 with respect to u? Not me, but you. U. Very good. Minus the next one. U plus 1 is the inside function. It's in the denominator to the first power. Its derivative is 1. We're not off by anything. This becomes the natural log of the absolute value of u plus 1 plus c. And this would be a horrible place to stop. You've done u-substitution, you've done long division, and you stop right there and you don't get credit. Because it's an indefinite integral, we get an indefinite answer. If it started in terms of x, we need to finish in terms of x. So, the ultimate question, what is u? Square root of 2x. We better plug it back in. Square root of 2x minus the natural log of the absolute value, the square root of 2x plus 1 plus c. So again, maybe just outside the scope of an AP exam, unless they tip you off as to what the substitution is. Yeah. Oh, yeah, let's try that. Based upon what we did over here on method 3, we're like, how'd you know that could have been an arc sine? Let's do that same thing over here. Exploring different methods. You could have said, hey, maybe this is an arctangent, hey, right? No radical. So let's see. If a squared is 1, then a is 1. If u squared is the square root of 2x, then u would be the fourth root of 2x. Now, is the derivative of the fourth root of 2x another factor in the problem? No, because there's actually no other variable assistance going on here. So, not a bad thing to try based on the previous example, but it doesn't work. So, yeah, good eye. I'm glad you brought that up. Because that's what it comes down to here, comparing all the methods and kind of getting proficient at the nuances, right? That's what makes you a pro. Which I guess, no, that's not what makes you a pro. Sorry. What makes you a pro is getting paid to do integrals. Is there such a job? Maybe. I get paid to do integrals. Right? And the unit circle, right? But I would do the unit circle for free, right? And integrals. Okay. How are we doing? We got lunch coming up. Okay, so we're going to finish after lunch. We got u-substitution. If you understand D and E, once you are given what u is, that's great. But in terms of what y'all are responsible for, linear inside functions, okay? Typically linear inside functions that are multiple terms, mx plus b style. It's linear and you're off by a variable. Change the variables, expand, integrate, and then substitute in, unless if it's a definite integral, remember, and you change the intervals of integration, then you can just evaluate it in terms of u and never look back. All right, any comments or questions on anything through example 24? We got 2 examples left after lunch, example 25 and 26, but each example has multiple examples, so it's kind of not really true, but anyway. Yeah, it's National Opposite Day, which is a really hard day to celebrate all day long, right? Remember in elementary school, you'd be like, it's opposite day, you're stupid. Right? So anyway, here's a phrase that makes sense on National Opposite Day. I spent all of last night just festooning and decorating the house with all my opposite day directions. The decorations. Directions, that's the teacher in me. Okay, that kind of ruined it, didn't it? Yeah. I spent all of last night decorating my house with National Opposite Day decorations, which of course means I didn't do anything, right? Yeah, and that's a way to celebrate, right? So anyway, I'm going to stop right there and try.